This lecture on tall building economics is one of the high-rise issues series in the Sustainable Tall Buildings degree course at the University of Nottingham. The podcast is for private academic use by students and not for broadcast or commercial use of any other kind without permission. The podcast is not a full lecture. It is a quick breeze through the essential ideas in the slides to help students with revision using the PDFs of the original lecture. This picture is of Manhattan, which epitomizes the high-rise city. The other one being, of course, Chicago, where tall buildings started. Going back to the earliest days, there have been aspirations to build tall, whether they were driven by prestige, religion, or density, as you see here, or even manufacturing. The pagoda, the Roman tenements of Ostia, the Italian palace, and the factory or cotton mill of Industrial Revolution England. The modern tall building era starts in 1885 with the home insurance building in Chicago, but very few people realize that at the same time there were buildings nearly as tall with metal frame built for residential use in New York and another one of mixed use in Chicago, the Pullman building. Why did this happen? Well, there was a period from 1870 to 1900 of manic technological innovation and urbanization and immigration to America, a quest for profit that has never been seen before, but could be said to be echoed in China at the moment. The things that were really changing for tall buildings were the inventions such as the elevator, the steel frame, the concrete frame for fireproofing, AC electricity, the light bulb, telephone invention, universal postal sorting, the typewriter, increasing density, a growing middle class, urban transport systems based on electricity such as the tram and the train, and of course the first clients who could need tall buildings would be insurance companies. Most of the first tall buildings are insurance. What do we mean by a tall building? Very quickly, the CTBUH defines tall building by several ways, one of which is simply, is it high relative to its surroundings? Does it contain technology that is representative of tall buildings, such as special elevators? Is it higher than it is wide? And if it's extremely high, does it contain special protection against wind and earthquake? We also make a difference between functional tall and iconic tall. In the first period of tall buildings, they fitted their site pretty tightly, and they had light wells, and of course no air conditioning and very primitive light bulbs. So they had large windows, masonry walls, and daylight cores, and fresh air ventilation, although they already had primitive forms of mechanical ventilation. This system of defining generations was devised by Philip Oldfield and Dario Trabuccio. After 1916, there were zoning laws in America which tried to improve the quality of daylight in the streets and required buildings to be set back or to get smaller as they rose taller. And this produced a ziggurat-shaped building with a centre core, but they still filled the site entirely. If you walk around the Empire State Building, you won't be able to see it because it has very tall podium buildings which obstruct the view of the tower. The third generation started after the war with the development of glass and air conditioning and Mies van der Rohe was the philosophical tutor of this movement, and SOM were the driving force as a major practice with some of their great buildings. We had cheap energy, air conditioning, plenty of steel and glass, and there was a belief in breaking away from Art Deco and going for the pure beauty of pristine shapes in the sky, pure cuboid forms. Because of solar gain, the glass was almost always darkened or mirrored, but it was always single glazed, and it needed a lot of artificial lighting indoors, which reduced daylight. As we moved on in the late 70s and up until the present day, we are far more conscious of energy, so we have double glazing and some double skin facades. We take much greater effort to control solar gain with louvers. We try to bring in natural ventilation, and we have other variations on double skin facade. But one should say that the previous generation and this generation seem to disregard the climate, and you will find fully glazed buildings in Singapore, Jakarta, Shanghai, Manhattan. Everywhere you see these buildings, and they do not adapt to their climate fully. Going on to the fifth generation, we have buildings which are minutely considered in every way for their climate, and will also integrate many technologies to make them more eco-friendly, such as bioclimatic design concepts of ventilation, daylighting, even passive house concepts for insulation, facades which save energy or generate energy, thermal mass in the floor slabs, lots of greenery incorporated into the building, ventilation, daylighting in atria, and quite often mixed use instead of being single-use office buildings or pure residential. There are numerous examples in this generation, and some of them are so extreme in their application of technology, we might even call them sixth generation. The activity of tall buildings is moving to Asia, especially to China, as this chart shows, dated 2010. The Far East is the greatest area for tall buildings, which is Indonesia, Taiwan, China, Singapore, Thailand, Japan. And on this diagram, the red stripes are North America, and the only European example is in Moscow. We should remind you of the difference between tall buildings. The ones like Burj Khalifa in Dubai are exceptional and not typical. And what we are concerned with really is the majority, the millions of tall buildings of reasonable height, which accommodate vast numbers of people working, living, shopping and learning, and are responsive to the 20th century context of population, density, transport, etc. One of the most seminal books on early history is Form Follows Finance by Carol Willis of the Skyscraper Museum. She writes up until the end of the Art Deco period and makes the point that there was a kind of development craze in New York to build profitable buildings almost regardless of having a client. But the shape of the buildings was pretty well the same, whatever was inside it. The form was defined by what the site could take within the zoning law regulations. The old form follows function doesn't apply with tall buildings. Something like the Empire State Building was designed as a pure mathematical planning exercise to see what would fit on the site before the architect even got invited to start wrapping a wall around it. This is an example of a contemporary design in the Hudson Yards in New York, where the Chinese-style skyscraper, as they call it, is predicted to be built on a 1,000 square metre site, a pocket tower, which cost, the site of which cost $110 million for 1,000 square metres. When you have land so expensive, you must build tall to get your money back. And you must also build mixed use. You need retail and offices and high-end residential to pay for the high cost. So economically, a city which is not under high population stress can always build up to 7 to 9 stories. The average height of buildings in Bloomsbury, in Paris, in Berlin, in Barcelona, and much of Manhattan, and they achieve high density. I should say also much of Hong Kong is up to 9 stories. But as land values, population, wealth and transport push harder, buildings have to go higher. Every time a building is decrepit and replaced, it must be taller than the previous one to get the money back on the cost of acquisition. As you go higher, the building can be thought of as a vertical cantilever, subject to wind loading and seismic loading potentially, with a risk of sway in wind loading, and you can build as you like up to 20 stories, even with masonry or a rigid frame. You need to try harder up to 35 stories, but your costs are still under control. Once you go beyond 35 stories, the cost increases hyperbolically. So here is a picture of Wan Chai in Hong Kong, showing the older buildings, which are all 9 to 12 stories. And when they get replaced, boy, do they get replaced. These massive buildings around them are over 200 meters high. As you go taller, the economics get worse because the relative core size increases relative to the floor plate as the building gets narrower. And your costs rise because everything, structure, facade, core, MEP, the foundations have to be safe against failure. With every 100-meter increase, there is a hyperbolic increase in cost. Having said that, the economies of scale allow you to invest in special structure, special elevator systems, technologies, renewables, which is a good thing about tall buildings. Existing tall buildings have cost a lot to build. If after 30 years we wonder what to do with them, we must consider that it could be most uneconomic to knock them down. Maybe we should refurbish them. You see here that Hudson Yards is what is being built over the Penn Station. Rail tracks. There is no way, with the massive investment in roofing over a working railway, there is no way you could cover this with buildings of average urban height. So I said that a building is like a cantilever. It's proportional to the square of the length. The bending moment is proportional. And the same thing applies to the building, approximately. The cost and the complexity increases according to the square of the height. The land is expensive to put together. There are very high initial costs in negotiation, and that's just before you get started with a natural building. There are massive amounts of design required to get the building right because it will last 50 years or longer. And there are what are called externality costs, which is the surrounding urban structure, the roads, the underground railways below it, the relationships to open space. And it can take something like 10 years to get permission to build tall. when you have to do so much work with consultants and city governments. There are very high costs up front with professional costs, many people required to take part. Having built a building, you don't just sell it, you actually get a continuing income from it. Even if it is residential, there are high monthly maintenance fees and charges. There is a revenue stream for the owner, even for things like parking spaces, which are a good source of income, but they should almost always be underground. One thing it seems is that good design is worth paying for because you are building something to last for a very long time. And marketing comes into it, that if it's well designed, it's easier for the developer to get tenants, and it's almost always paid off. Good clients are aware of this and will consider long-term revenue and marketability of the building over the long term. But one should always remember that after 30 years, there may be a complete rethink about the function of the building. Maybe it should be converted to residential, but can it be knocked down? It is far too difficult to get your money back. If it is already tall, the only way to get your money back is to build even taller, and that may not be possible for urban context reasons. One thing to remember is that commercial buildings have a completely different cost and occupancy from residential ones. They need far more elevators, wide spans, whereas residential buildings are partitioned, which can be structural partitions, fireproof partitions, which change the economics completely. Residential ones are also less subjected to recession because people don't tend to move in a recession, they sit tight, whereas office tenants will often panic and leave. So this is an interesting paper from the CTBUH. It's a 2-page paper. I'll quickly run through you. It shows you here the typical elemental costs between a typical low-rise, a high low-rise, we're talking about 9 to 12 story or up to 20 story, and a high-rise. And you can see here that the costs expand on all those because of extra precautions required in building tall. MEP is about the same. Higher cost in lift and escalators, as you'd expect. Whatever you are building, the shape and geometry will have a big impact on the cost, the iconicity, the slenderness, the size of the floor plate that you can achieve affects how you can market the building. Where do you put the core? What methodology is for building it? Are you in a city centre and having to build it always between midnight and 6 a.m? How complex is the facade? We don't like big flat glass facades anymore. We expect more articulation, complexity. Also, we expect environmental strategies and sustainability features in the building, which will increase its cost but will extend its sustainable life. You consider the site constraints, including the seismic consideration. You consider the long-term market conditions for operating and running the building. And the vertical transportation strategy is important. If you have a single-use building, you can of course plan elevators to serve that one purpose, but in a mixed-use building you are considering retail, parking, servicing, residential elevators, maybe shuttles to a club on the roof. All sorts of complexities come in with vertical transportation. So offices tend to cost more than residential because they have a higher standard of finishes, longer spans, and the tenants expect to get a finished product whereas residential, a lot of the furnishing is done by the occupants. And there's less MEP in residential because the occupants can open their windows. Also, you can't fix down the price of a tall building because it depends where you are. In China, there is a lot of cheap labour and a great deal of expertise at building tall buildings, so they are cheaper. In London, you have very, very high operating costs with the city around you being congested, and builders are, I'm not saying that they're unexperienced, but the thing is you have to get in the queue for the really top level contractors to build your building. You have a higher substructure cost because under London you have a whole mass of tunnels. So this displays 5 different locations: New York, Melbourne, Shanghai, UAE and London, with London being far and away ahead in terms of the cost of construction, especially in the city centre, which must run 24 hours and does not like heavy traffic driving through their streets. This slide summarises some of the key ideas about superstructure, facades, the wall-to-floor ratio, the construction costs in different locations, the cost of becoming iconic instead of functional or residential, and the triangle of the fundamental drivers of time, cost, and area. Another important concept is net to gross ratio. The gross is the total area of the building. The net is what you can charge rent for. So you can't charge rent for the thickness of the wall or the amount of core or the toilets or the service shafts. So you try to get a ratio between those two, and something like 60% would be considered very inefficient. 85% is only possible with a smaller tower of a single function offices, and most buildings will go for somewhere between the two. Owner-occupiers, like banks, are often happy to get a less efficient building but with a higher quality of space. A speculative building will have the client asking for a maximum ratio because they're not concerned with quality. So theoretically, as you're multiplying site with height, more floors would appear to be more profitable, but this is not always the case. The higher you go, the deeper you need foundations, the bigger the core, the less floor space you have for renting. The facade is larger relative to the floor space. The M&E are greater. There is a hyperbolic cost increase. And you need to consider how long it will last for. The building may only take 30 years to pay off, but it will be part of the city for maybe 100 years. So you can see here a document by James Barton illustrating how, as you increase height, you lose net to gross ratio. This also shows that one of the more expensive parts of a building, the facade, there is more of it as you get taller, quite logically. As you go taller, the building size must get larger in plan for stability reasons, but people like high floor-to-floor heights, and there will be a very expensive facade, and the upper levels of facade are getting more battering from the wind, and there are more issues about safety with a swaying building. One of the most important decisions you make is orientation and core locations. This diagram is from Ken Yang's book, and it shows the classic centre core building with options suggested for tenancies, multiple, single, etc. There are often advantages to having two cores, like a large core and a small core. If you have a single offset core, you can subdivide the floor, but you have longer escape distances and the risk of dead legs. And you also have a higher facade cost, because the facade needs to balance out the stiffness of the core. Sometimes you have an atrium core, where you have what might be called a twin core with more space in the middle, but this is going to improve the quality of environment but will reduce your net to gross ratio. One thing to remember is that you may be the primary architect, but you may not be the fit-out architect. For example, with offices, you should always ensure that there are escape routes and options for laying them out as open or closed offices, but it will be another architect, the fit-out architect, who designs the details of that layout. It should be remembered that historically there have been surges of tall building, surges of speculation and land value, but they have often been followed by depressions. There were depressions in the 1890s, in the 1930s, in the 1970s. We are now entering a period of unprecedented tall building activity, especially in Asia, but even China is feeling anxieties about how long this growth can be kept up for, and they are even building cities which nobody lives in yet, but which are for expansion of future populations. At the end of life, some buildings are either faulty in their structure or they are simply in the wrong place. Tall buildings tend to have very good structure. Their errors might be in their quality of the MEP and in their facade. They may simply be better off converted to another function, like residential. This is the King's Reach Tower, which is now called the South Bank Tower, which was a company headquarters, and it was deemed better to convert the whole thing to luxury residential and build a much lower level podium to contain modern offices and retail, which would be more marketable, with a park on the roof, and convert the tower to residential. But to make the tower work financially, they were permitted to rise it another 40 metres. And in return, there were what's called externalities, where the developers paid money for improvement of the local area, which of course will improve the value of their flats. With refurbishment, the first thing you consider is MEP and facade. In the case of office conversion to residential, the office core is much larger than you need for residential, so it is much stronger, therefore capable of being extended vertically. The only reason you would demolish such a building is if it has structural failures, such as Draper's Garden in London, which was built with high alumina cement and would not last another 50 years. If you must take a building down, this is the tidiest and cleanest way. It's called top-down. You try to demolish the building with minimum damage to surrounding urban fabric and minimum dust, and minimum traffic as the red debris is carried away. You try to recycle the materials. This is the DESP method, which takes longer than blowing the building up, but does so in an urban environment without causing pollution. Thank you for listening.